All right, let's get started. So happy Thursday. So couple of announcements before we get going in our lecture here. So of course, don't forget the exam is next Thursday. Our first midterm. So like I said, we'll review on Tuesday like we normally do and then take it on Thursday. And of course, let me know about alternative exam locations. We can also send it over to the other campus if that's more convenient for you. And then also on the radar, I'll just remind y'all that we have our field trip May 12th, and that's a Tuesday. And so just make sure you get permission slips filled out. Let me know about guests so we can get those approved and all those sorts of things. Other questions, comments? All right, so let's go into lecture a little bit. Oh, wait, I forgot. Didn't we leave off with a... Did we leave off with a problem in here or no? Am I thinking of my other class? Sometimes I mix up our classes. Okay, I thought we had left off on something. Where'd it go? Where are my oxidation states? Oh, I'm like... There we go. Okay. So we left off here. That's right. And we were trying to determine oxidation states. So let's go over this one. And so I'm just starting at the methyl group, right? Pulling things apart and then giving all the electrons to carbon then in this case. So it gets half from this one. Then 1, 2, 3, 4, 5, 6. So what do we get for our oxidation state of this carbon here in our methyl group? So right, 4 minus 1, 2, 3, 4, 5, 6, 7. So what does that give us? Can't tell if you said it. So chat has it as well. So -3, right? And then hydrogens, these would all be 1 plus. And then going to this carbon, so again, splitting all our electrons evenly. So it gets 1, 2, 3, 4. So what's the oxidation state of this carbon? So right, pull it off. 1, 2, 3, 4. So 4 minus 4 gives you, so 0, yeah. So we have 0 for this carbon. Okay, so now we're looking at this one. So again, split that evenly. So 1, 2, 3, and then it gets 2 from hydrogen. So 4 minus 5 gives us, so -1. And then this hydrogen is +1 to balance. All right, so now we come over here. So this could be a little tricky, but right, so okay, nitrogen is closer to fluorine, so more electronegative, so it gets all of those. So it gets those, but then it's going to lose to oxygen, right? So I'm just kind of trying to pull everything off now. All right, so now we can do nitrogen. So nitrogen is just left with 2 then. So then we have 2, or excuse me, 5 minus 2. So what does that give us for nitrogen's oxidation state? So positive 3. What are the two oxygens and end up being the same? So 6 minus 8 on both of them. So did we get negative 2 for both of those oxygens? And that does match, right, what we expect for oxygen for its typical oxidation state. All right, so then we're at this carbon, but remember it lost out on these two, so now it just has 1, 2, 3. So 4 minus 3 gives us plus 1. And then now we're at this carbon, so it takes all the hydrogen ones, right, but splits those. So we have 1, 2, 3, 4, 5. So 4 minus 5. It's negative 1, right, for that carbon. Plus 1 for hydrogen. And then we see this just kind of repeated, right? So same thing, split our carbons, 1, 2, 3. 2 for hydrogens. So 1 plus on hydrogen, 1 minus on carbon. Same thing up here, right? 1, 2, 3, 1, 2, so there's 5, so 4 minus 5. Negative 1 on that carbon again, and then plus 1 on that hydrogen. Questions about that one or how to do the analysis or any other like metals that came up or anything in our practice? So we can always revisit this. All right, so now we'll kind of go back to at least a little taste of electrochemistry. And so we'll start it now, and then we'll kind of go through it again. Sorry, I realized I put my notes on not the correct one. So midterm Thursday, field trip May 12th. Okay. And yeah, so going back to this one, sorry, I keep losing where we were writing. Yeah, on an exam, we would want to still write out plus 1 for all these hydrogens and, you know, minus 1 for all these carbons. So even though it gets pretty repetitive, yeah, we want to write explicitly what it is. And, you know, just in case to distinguish from a metal hydride anyways, so we should still write out that hydrogen is always 1 plus. Other questions before we... Like I said, we'll kind of start electrochemistry, but then really we'll do more with it in chapter 25. But just kind of the introduction of electrochemistry. And so your lab's also a good introduction, but we'll talk about what your lab is doing versus what the demo is doing, and hopefully kind of put everything together a little bit. And so electrochemistry itself is just the study of these redox reactions that produce or require an electric current. And so some of this, of course, gets into the practicality of like, well, how do you make sodium metal or alkali metals or produce fluorine gas? And well, for a while too, that was like part of the challenge of like how do you physically do like the electrolysis of fluorine or fluoride, right? Like a molten fluoride salt to make fluoride gas, and that literally killed people in the study of that or pursuit of that. So just things to keep in mind as we study this. And so we'll look at these reactions. So we have the conversion between chemical energy, and so we're going to kind of, again, hopefully start to pair the math behind it, because this is what we want to understand, is that sometimes, just like in a battery, we have chemical energy, right? So that's stored as our chemical potential energy based off of our reduction potentials, right, of our paired anode-cathode reactions. And that would take place, right, in our electrochemical cell. So just converting that energy. And these spontaneous reactions then are just called a galvanic cell. And so, right, you can also think of, you may have done the like lemon battery experiment. I don't know if you guys have done that in high school or whatever, where you just proving, right, that there's some sort of electrical potential in that. And again, we're going to see that in the demo. And so you could also make a voltaic cell, right, with, I don't know if you've done those coin cells with pennies. That's always a good one, just to, again, introduce yourself to the topic. So if you're ever bored in lab today, we could play around with these sorts of things as well. But okay, so then this leads us to essentially, right, battery technology. So that's all batteries are, is, right, these electrochemical cells. And of course we won't get into what's in them and blah, 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 but right, that's of course what makes it irreversible or not is, of course, you have this, right, normal spontaneous reaction. I think like typical older cells are like manganese reactions, and then now they're all these like cobalt intercalated with, I forget what materials, but right, it's just like whether those reactions are reversible or not. And then, so what we did in lab though, or what you will do today, is, well sometimes we have these non-spontaneous redox reactions. And so of course those can be made to occur in our electrolytic cell by the addition of electrical energy. So that's what we're doing, right? Just going back to kind of the first water splitting reaction. And so let's kind of look at, I want to take a step back before we get into like all this text, because I think if we look at kind of two scenarios and piece them together, it'll come together. All right, so let's look at, like I said, the challenges of trying to make our sodium metal. So let's put electrolysis of sodium metal. And we'll put right from molten sodium chloride. And so this is also kind of different, right? Again, just like thinking about physically the differences is, well, obviously this is not taking place in water, and we'll see why for other reasons, which we're kind of like teased at in your lab, but I kind of want to make sure that we all understand. And so, right, this is air-free system, and so that's also why we're able to do this, but it also depends on, right, kind of eliminating side reactions is what I'm getting at. And so again, the whole point of electrolysis is to take a non-spontaneous process and then, right, get it to go. So I think it'll make more sense if before we start kind of drawing out the diagram of what's going on, let's think about what we want to do chemically. So we want to take, right, sodium chloride and again do electrolysis to make sodium metal. And then of course that will also produce chlorine gas as a consequence. But now let's look at what that is going to cost us. And so let's separate our half reactions. And so we have sodium then, so a sodium cation has to pick up an electron, right, to make molten sodium. And then our chlorine, or chloride, excuse me, is going to form chlorine. So, right, being oxidized and then losing our electrons. Okay. And so let's, again, give us context to this process. And so we've kind of been, we'll go over the text and kind of get there. But basically, what we've established is, okay, we have this standard reduction potential, right? We saw this in our lab. So it's part of your introduction. And so again, this is just telling us the potential of these reactions. All right, so let's look at what we want to do then. And so now I'm going to scroll around. And so here's sodium at the bottom. But of course, we need to flip the sign. So like I kind of mentioned in lab, and again, right, we're all getting up to speed. It'll make more sense by the end of like chapter 25 for sure. But okay, so this is the reduction potential for this process, right? And they're called standard reduction potentials since they're just written in the reduction form, right? So all the electrons are on this side. And so this chart kind of gives us a hint. So again, how it's written is the more negative, we have our stronger reducing agents, if we kind of remember, right, our workhorse, versus up at the top, we have our stronger oxidizing agents. Okay, so now we copy the process that we want to do. So we're going from sodium, we want to plate out sodium metal, excuse me. So right, we have our sodium plus our electrons, so that's negative 2.71 volts. And we'll write that because that's in the correct reduction form. So this is, and we might have small discrepancies in numbers. So negative 2.71 volts. And so this is telling us that this is not a favorable process. Again, we'll kind of get there in the math of it. But basically, you need a positive voltage, but we'll add them together. So now I've kind of jumped the gun on things. All right, so now let's go to chlorine. And so again, looking at what we want to do. Where's my chlorine gas here? Oh, it should be at the top. Here we go. Except we're going in the opposite direction on this one. So sorry. So this is the one where we need to flip the sign, right? Where we're going from chloride to chlorine gas. So it's going to be negative 1.36. All right, so then what we want to do, and so your book or like other resources sometimes have like other rules for how you figure out the reduction potential. So I find the easiest thing to do is just, again, order your reactions in the way they need to go. So flip them appropriately, flip your signs appropriately. Now we can add these two numbers together. Sorry, let me fire up my calculator. All right, so now the overall process for this is negative 2.71 volts plus negative 1.36 volts. So that gives us about negative 4.0 volts total for this process. So what that's telling us is, like I said, we'll go over this more formally in chapter 24, 25. But okay, this negative sign is telling us that it's non-spontaneous as written. And so to make it go, we have to at least apply this much voltage. So kind of thinking back like to your battery, I mean, we did have a 9 volt, so we had plenty of voltage anyways. But that was part of like the pre-lab questions, is like, do we have enough power even to do it? And so we at least need a 9 volt. Okay, good. And so now let's get into the schematics and where everything occurs. And so typically by convention, so reduction occurs at the cathode. So we have reduction at the cathode, and then we'll kind of sketch out our battery. And then oxidation at the anode there. And then so we can draw our little cell diagram. And again, right, thinking about that this is really molten sodium chloride in there to again make it an air-free, water-free environment for, of course, the reaction reasons, but like I said, we'll compare a few other technical issues. And so then battery, and so this is, right, our electrode, similar to how we use graphite. So this could also potentially be like a graphite electrode like we're going to do. Actually, I don't know what they use physically. I'd have to look that up. But this is our anode, and then electrons are going. And then this would be our cathode. And so at our anode, right, this reaction is occurring. And so we'd be getting chlorine gas. And again, in industry, they'd of course be collecting this, right? That's valuable product. And then at our cathode, right, we're getting out our sodium is coming out. All right. And okay, so there's kind of an idea of our physical setup, but let's compare it. And so this is, again, kind of what the lab was doing. Is, well, what happens if we're in aqueous solution? That was part of the issue. And so now similar setup. So I'll draw it out first, but then we'll go to what the lab was kind of getting at. And so this time, so now we're going to be aqueous, so electrolysis of aqueous sodium chloride. And so again, this is similar to this is your lab setup. Now I'll say that. So this is a lab setup. So we have graphite pencils, right? Our anode again, cathode. And so part of the lab was like, okay, well, look at these competing reactions, right? What else could happen? And so that's what the pre-lab was, and what you maybe spent a lot of time was just like the prep for this lab. And so again, looking at our cathode, so we want to kind of compare reduction reactions. And so that's kind of what you're doing. And so again, in this system here, so we have, right, sodium chloride, but then of course, like we said, we're aqueous now. And so now there's a bunch of aqueous water just floating around. So, right, that is a competing reaction. And so that's what you, again, did in lab. And so now let's look at our standard reduction potentials together. So let's see if I can find it. So here's our reduction, and we know it's a reduction of water since they're on the same side here. So 2 equivalents of water plus our 2 electrons. And then this is also, again, part of like what the lab was hinting at, but it's good to kind of re-go over it or go over it if you're not there. So then, okay, evidence for that is we would see bubbling, and then you can use your phenolphthalein indicator or another appropriate indicator, right, to search for the presence of hydroxide. Or you could pick something like a universal indicator, but the phenolphthalein works well. And so then, and this was what the lab had you do, is okay, so then let's rewrite our reduction potential of sodium from before. So that was negative 2.71 volts, right? But then when we looked at the water, oops, sorry, need my arrow. And so our water, and this is what your lab was saying, is so this process, right, is less negative, and so that means it's going to happen first. So it's much easier to perform this, and so in reality, right, this is the only product. And of course, not to mention just the physical issues of if you were to somehow plate out the sodium, right, it would be like reacting with the water as well, so that certainly doesn't help anything. And then I believe there are a few discrepancies. So let's look at the anode, and we'll talk about, like I said, the discrepancies you might see and kind of why that is, or at least a little to the why. And so again, repeating the process. So anode is oxidation is occurring at the anode. And so we want to look at our two reactions. So of course, we have, right, the chloride from before. So I'm just going to rewrite that. And then, so let's look at our water oxidation. Trying to find it. Okay, here it is, right? So we have water and our electrons on opposite sides. So there's the oxidation of water to form O2, and then it would also make acidic conditions. So in theory, you could select an appropriate indicator for that. And so now, right, we're going to flip that sign, though, because I need water on the other side, right? We're splitting water. So I'm going to flip that when I rewrite that. So again, our other competing reaction is our water oxidation. That makes O2 plus hydronium ions and electrons. And again, that happens at negative 1.23 volts there. And so this is where you might have observed a minor discrepancy yourselves in lab. I think you had maybe not chlorine, but iodide, if I remember correctly. And I think the reduction potentials were pretty close. And so you may have concluded that you would only get the water, but there is still a chance that you may still form some of these chlorine ions in this case, or like I said, in lab, you might have seen some brownness from the iodine being formed. And so just watch out for that. So even though, like I said, we expect this from our reduction potentials, there's a little bit more to it, which, I mean, honestly, I myself, like, don't fully understand, but it has to do with, like, the amount of ions in solution as well. So we'll look at some equations in chapter 25 that might help us, but, right, it's also dependent on concentration and probably a little bit of Le Chatelier's principle. So the fact that we're, like, kind of saturating it with our ions, right, is kind of helping drive this reaction forward. So you guys can, again, let me know how it turns out in practice. But that's the quick and dirty there of electrolysis. All right, so then I did bring a demo. And so then we kind of want to shift or think about the comparison, right? Well, let's look at a spontaneous reaction then. So building a galvanic cell. So let's look at the math. And so again, looking at our reaction, so what we're going to do, and we'll build it, like I said, we'll build our demo. And so let's look at what we're doing. And so again, I'm just going to get our appropriate half reactions. So we need our zinc going to zinc, 2+ there. So let's look at our standard reduction potentials. So there's zinc, so I need to flip that. So that's going to be positive 0.76. And so let's look at this next process. So copper 2+ plus 2 electrons, right, to give me copper. So trying to find it. So wrong reduction potential, right, that's 1 electron. Sorry, I keep getting distracted by the 1 electron process. Where's copper? There it is. I'm just blind, apparently. All right, so copper, and now I forgot which direction we're going. So we want to land, so we're going with copper ions, and then landing with copper metal. So it is in the correct direction. So again, positive 0.34 volts there. Okay, so now this is telling us, again, our theoretical potentials. So we'll add these now that they're appropriately flipped. So 0.76 plus 0.34. And so that gives us about 1.10 volts. And so like we said, we'll look at some more equations in detail, but this is assuming, so like I said, I'm going to do this, but if I don't hit 1.1 volts exactly, it's because something is off in my ratio of my molarities slightly. So we'll find that in our equations, that the molarities have to match. But like I said, that's chapter 25. And so, right, we can look at this redox reaction. So we'll look at this. And so this is just pairing that together, obviously, right? So if you put our zinc metal in here with our copper solution, right, this is going to also spontaneously occur. But what we want to do for a galvanic cell is to split this reaction, right, into our cells. Otherwise, it will just eat our metal. And so I'm going to try to sketch this out. All right, so let's sketch out our galvanic cell now. And again, right, this is spontaneous. So positive voltage, so it helps us remember. And so now, so we'll sketch this and then you'll see me build it and hopefully not screw this up. So we have our zinc metal and then we should have our beaker here. So there's our beaker using zinc. If we didn't have a metal, for example, if we were using like a iodate solution, then you could use like carbon again as your electrode. And then this will be a zinc 2+ solution. So I brought along zinc nitrate for that, just anything soluble. So it doesn't matter, right? Just as long as we have the correct 2+ counter ion. And then we'll hook up a little wire to it. So I'm going to hook it up to a voltmeter. I wasn't fancy enough this morning to grab, because you could technically hook it up to a light source. but I'll put it into our voltmeter so we could measure it across. I'll put light, and then this will go into another beaker, copper 2 plus solution. And so then let's look at our, again, by convention. So our zinc then, right, so zinc, just to reiterate so everybody's on the same page. So zinc is undergoing oxidation. So this is our anode again, formally, again, where oxidation is occurring. Electrons are still flowing this way. So copper, and then again, right, reduction is occurring at this one, which matches. So reduction, cathode, and then, salt bridge goes between them, so those ions flow. All right, so let's do it. Let me get my camera set up. Okay, so my camera, yep, okay, camera's still functioning, perfect. All right, so let's build it. I thought I'd grab, here it is. And so I do have to give some credit to Brooke. So this demo did start off as like a project. So we were asked last year by the Girls Rock organization to do a demo. So then we came up with this battery demo, but that of course meant that somebody had to physically test it and troubleshoot it and make kits for tons of middle schoolers. So I will have to give Brooke a large hand and shout out in troubleshooting this. All right, so what we found and what I'm trying to do right now is I'm massacring this cheesecloth because it works as a pretty good salt bridge. I was like, speak of the... That was not time. That was not planned. Oh my gosh. So yeah, now I'm just soaking our salt bridge in some pickling salt. That works fine. I'm trying to get some extras just in case we want to couple it. And so, okay, let's go. Let's look at our cell so we could build this correctly, right? And so we'll just copy our design here. Oops. Sorry, trying to make good production value here. All right, so let's start that. So we have, right, one cell. So we'll start with our zinc foil. And then I'm going to go ahead and put a wire on it so I can hook it up to my voltmeter. So zinc, right? So again, putting the appropriate counter ion solution. Where's our camera at? So I'm just putting enough to submerge it. Nothing too technical with this setup. Like I said, we're not getting, you'll see with the math how we can get more technical, but I'm just trying to do our quick setup. So this needs to go to my voltmeter, which now I realize I should have double checked I knew how to use a voltmeter. Just exposing these tips, they're pretty small. And we'll see if I hook it up backwards. Sometimes I do that. All right, so copper, metal. Grab. And then, let's see. So we haven't completed our circuit. Oh, I stuck in the wrong thing. So copper, and then copper sulfate. Again, just enough to submerge there. And so now we'll take out the cheesecloth that has been marinating. Oh, just trying to make it to a little bridge. Make sure you connect your circuit. Let's see, can we see that? Not the best camera work today. All right, so there's our completed circuit. And then, of course, I didn't turn on my voltmeter. Uh-oh. Oh, sorry. I'm just being really stupid. Okay, so I think I have it flipped, which I thought I might have done. So let me flip these. All right, and so can you read? Oh, you can't read that number. So like I said, I wasn't sure if we would make it to our theoretical 1.1 volts. Because like I said, I expect the molarity to be off. I already picked 2 different molarities. I was just grabbing what's around. So this is technically 0.08, at least that's what it says, versus 0.1. We'd have to go back when we do chapter 25 and see if this matches theoretically or not. But then what's kind of fun, if we were wanting to continue this, is of course, right, you could connect them in series and increase the voltage. So I don't know if people want to do that. People are excited or not excited. But yeah, so we can connect another one. So let's see if we can do it. So I'll start by making another cell. So let's see, zinc nitrate. Let me cover this at least. Oh, hang on, let me get an alligator clip before I lose that zinc. Zinc, copper. Oh, sorry. Need an alligator clip. Bridge. All right, now let's see if I don't screw up the... So this one needs to go to here. And then take this over to this one. Yes. And so now you can tell that we have twice what we had before, basically, of about 1.7 now. So just doubling it. And of course we could keep going, but I'll probably stop there for now unless people want to come play with it. You're also welcome to come play with this yourself and chain them up. But that's a good, like I said, demonstration of now, right? This is, again, our spontaneous cell, so positive, right? Positive overall, right, potential. So again, telling us that once we pair these 2 reactions, that yes, it's spontaneous, versus, again, right, our electrolysis, where we have to force our non-spontaneous reaction. And so, like I said, we'll kind of get into that. So just kind of wrapping up. So we'll re-go over all of this in 25. And again, kind of like you've gathered to we've already introduced this standard reduction potential, but basically, right, we have to have some standard of comparison, and so usually this reduction of hydrogen is used. And you always have to compare it to some standard electrode. So for example, like ferrocene is often used for like inorganic chemists if they're trying to test their little electrolysis setup and measure the reduction potential of anything. You just compare it to some standard. And so again, that's how all these were derived, right? So again, that's just our standard reduction potentials that we've been using. And so we'll go over kind of this in more detail. And so just solving our cell potentials. So I don't like these equations. I just like, again, kind of adding them in the way they are reacting. And then again, we'll go over this again in 25. So the main thing is just our oxidation states from 24, but just again starting to see, okay, if they're higher on the table, right, they tend to be our oxidizing agents, so they want to be reduced. Lower, then again they are oxidized. So just continuing to like put that in context in your brain. So again, like fluorine is up at the top, and then all your alkali metals are at the bottom. All right, we'll end here for now. So I'll kind of leave my demo up for a little bit if you want to play with it. You could always try to get a third one in series. And obviously, you could keep playing with different permutations of metals and everything. Right. Oh, and then of course we have the quiz. Almost forgot about the quiz. So I do have the quiz, so I'll hand that out as well. But again, feel free to poke around with this. I'll leave this up for a second. All right, hand out the quiz. Let me know.